Okay, today we're going to be talking about triple integrals using spherical coordinates. This video may look a little different than all my other lecture videos because I had a technical issue with my camera in my last class, so I'm sitting here doing this video without a classroom full of students. It's just me, so if it appears that I'm not talking to the class, that's what's going on. Okay, so spherical coordinates. We already know that when we're looking at triple integrals, we are usually trying to do a triple integral over some region, let's say E, of some function of x, y, and z with respect to volume. And we've seen there is one way we can do these without using Cartesian coordinates, and that's to convert this to what we call cylindrical coordinates. And in that, what we do is we replace x, or we substitute x as r cosine theta, we let y be r sine theta, and we let z just remain z. And when we do that, this new integral gets transformed over to a new triple integral, and our region is the same region, right? But it's just represented with a different coordinate system. So I'll just call this S. And now we change x to r cosine theta, y to r sine theta. Z will remain z. And then very important, because we're making this conversion, we have to put r, and then it's going to be something like dz, dr, d theta. And the order here may change, but we have to insert that r because of the conversion. Today, what we're going to do is a new type of coordinate system, spherical coordinates, and the conversion there is going to be different than this conversion. All right, so let's talk about not only what that conversion is, but let's talk about the spherical coordinate system in general first. So for spherical coordinates, if we're going to convert from Cartesian to spherical, we're going to let x be replaced with rho cosine theta sine phi. Now, some people pronounce this phi, some people pronounce it phi. You might hear me saying both. Rho is like r, like the radius. So this is like we had r cosine theta back for cylindrical. Well, for spherical, it's going to be, we use rho instead of r. Rho cosine theta sine phi. Y is going to be rho sine theta sine phi. Z is going to be equal to rho cosine phi. And then we have an identity here that phi squared equals x squared plus y squared plus z squared. So what does this coordinate system look like? Let me get back to my initial settings here. All right, so imagine that you have the XYZ plane, or sorry, the XYZ three-dimensional space. And imagine that you are, standing at the origin and you're looking straight up the z-axis. And you're pointing, you're orienting yourself where you're not only looking up the z, but you're kind of facing, if you look straight down, you'll be facing the x-axis. So here's the x-axis, here's the y-axis, here's the z-axis. So you're looking straight up. And then we want to get to some point that's out in three-dimensional space. So I'm looking up, here's the x-axis. I'm going to rotate my head down. The angle that I make between myself and the z-axis, that's going to be phi. So I start to rotate out, and you can hopefully see, if I rotate this, I am, I'm kind of parallel to the x-axis here. So I rotate out a certain angle, okay, from the z-axis, that's going to be phi. And then, once I've rotated out, I'm trying to get to some point, I'm going to now, here's the x-axis down here, I'm going to rotate myself this way at some angle, and that angle is going to be theta. So let me rotate this. So notice that what's going to happen, I'm going to start swinging out this way. Okay, that angle here between the x-axis and the ground there is going to be theta. And then rho is how far I go out. So rho is the distance to that point. So I can decrease this. Let me try and zoom in, see if you can see this a little better. It might be a little bit easier to see there. Come at it from this side. So there's my phi changing, and then there's my theta changing. So if you can imagine right now, if I just take this point, okay, so remember rho is the distance from the origin to the point. If I just take this point and I start letting theta change and make theta go from 0 to 2 pi, then what's going to happen is I'm going to swing all the way around. Okay, I'm going to swing all the way around. Are you subbing? Oh, okay. All right, I've got to stop this video. Okay, sorry, that video is going to look weird that it just cuts to this, but I got kicked out of that classroom. All right, so back to what I was saying here. If we rotate this all the way around, right, if I let theta vary, I'm going to swing all the way around. Let me zoom out a little bit. So you can see this point is going to come all the way around if I let theta go from 0 to 2 pi. And then if I change my angle phi just a little bit, so I rotate that point down a little bit more and swing my theta all the way around, and then just continue to do this, okay, let phi come down more, and even I can let phi go down below the xy plane and swing around. What I'm going to get in the end, all those points will form a sphere. So this might make a little more sense here. So notice if I change phi, I'm going to just move up to some point on the sphere, change phi, going to be up here some point on the sphere. And then if I change theta, it's going to swing me around the sphere. So all those points will create a sphere, which is why they call these spherical coordinates. So we do have some restrictions. The theta has to be between 0 and 2 pi. So when you're pointing, initially you're up, phi can come down, or phi can go between 0 and all the way down, straight down, which would be pi. So phi is between 0 and pi. That's this. And theta, which is this angle, can go between 0 and 2 pi. So you can do a full rotation there. And then rho can be, of course, greater than or equal to 0. That's the radius of the sphere. All right, now, if those are the coordinates, then here are our conversions. If we want to go from Cartesian over to spherical coordinates, it's a pretty complicated conversion. There's your x, your y, and your z conversion. So just remember that when you go to spherical, that's your replacement. See, with cylindrical, we just did r cosine theta, r sine theta for x and y respectively, and z just stayed z. But for spherical, we have those. Now those look like it might make it more complicated, but it turns out that a lot of these problems can become much easier by going to this coordinate system. Now here's another example of a spherical region. So let me see if I can kind of show you this. I'm going to show it to you from the back side. So what we have here is I've taken my phi and I have restricted it between two constants. And I can use, let me see, hold on. I have it written down here. C and D, alpha, beta. Okay. So if I restrict my phi between two constants C and D, my theta between alpha and beta, and my rho between A and B. So let me explain that with this picture. Now we're looking at this kind of from the side. So what I've done is I've said, all right, look, I'm going to start pointing out up the z-axis. This is going to be phi. What I want is to restrict my phi between two constants. So let's say that's C, and then I can let phi be anything between C and all the way down to D. So that gives me all of this swing of angle here. But my theta is between alpha and beta. So my rotation, once I swing down, I have to start rotating around like this. If I restrict my theta between alpha and beta, then you can see this would be alpha, and then swinging through here would be to beta. So I'm allowed to get phi between C and D, phi, between C and D, and then theta is between alpha and beta. And then I let my rho be between A and B. So rho is how far out I walk. So if I'm here, I can swing down, I can swing anywhere in here, and I can walk out only between A and B. So this would be A. So the distance from the origin to any of these points on this little surface here is A. And then anything on that outer edge would be a distance of B, and it's everything in between. So what you get is this weird looking solid shape, three-dimensional solid, which is really like a spherical rectangle. All your variables are stuck between constants. Now I can adjust this, which I will, just to show you some different variations. Let me make this a little smaller so I can see what I'm doing. How about I let my radius go from the origin out Okay, here's another region. Bring phi up a little bit there. And let me just swing this around so I can see what I'm doing. Okay, what I've done here is I've restricted in spherical coordinates, I've drawn a ball, a solid ball, but I'm just looking at the first octant of that ball. And let's say it has a radius of, let me change the radius here to about, let's make it 2. So, close enough, 2. All right, there we go. So there's that. That's a solid ball, but I'm just looking at it in the first octant. So let's talk about my restrictions. If I wanted to draw that, my restrictions would be, let's see, so phi is the angle from here down to the x-axis, which would be 0, right, all the way to, what, a quarter rotation, so that's pi over 2. So my phi is between 0 and pi over 2. And let me just double check that I'm recording right now. I don't want to go through all this. I kind of got scattered there when I had to evacuate that room real quick. All right, I'm good. So phi is between 0 and pi over 2. And then my theta is the angle on the ground here. And again, I am only in the first octant. So if I look at it from the top, I can see the angle. This is the x-axis. I'm swinging over towards the y-axis. So that again is a quarter rotation. That's going to be pi over 2. So theta is between 0 and pi over 2. And then finally, rho is the radius. Excuse me. Excuse me. And it's all the points from the origin out to 2. So it's everything in between. So my rho is bounded between 0 and 2. So that's what that region would look like. Now let's just see what would happen. What if I change it so that my rho actually only goes from, instead of 0 to 2, how about 1 to 2? So I'm only allowed to include points that are distance of between 1 and 2 from the origin. So I would have, let me change this to about 1. See how close I am to 1 here. Pretty close, close enough. So look what happened here. It's like we carved out this region inside, right? So it's like we scooped out everything that was, we scooped out a ball, a portion of a ball in the first octant, right, that had a radius of 1. So that's what these restrictions on phi, theta, and rho would give us that spherical region. So you can see this region is very different than, it's a lot different than a cylindrical region is, and it's different than a Cartesian. I mean, in terms of, it's easier to define this. It's very easy to define that region in spherical compared to, imagine trying to define that in Cartesian or cylindrical would be much more challenging. So whenever we have regions like this that we're trying to integrate over, it's natural for us to want to switch to spherical. All right, now let's talk about the actual setup of the integral. So if you have a region E, and you have these restrictions on theta, phi, and rho, then our triple integral will turn into, okay, so this is our conversion. We're going to go from alpha to beta, and I made it too big. Let's go 150. Okay, it'll go from alpha to beta, and that'll be our restriction on theta. And then it'll go from C to D, and that'll be our restriction on phi. And it'll go from A to B, and that'll be our restriction on rho. And then all you do is you go in the function, you replace the x with, remember what I said, we have to turn x into something ugly. Here it is. All x's will be replaced with this. All y's replaced with this. All z's replaced with this. And then we have this very important rho squared sine phi. That is kind of like, remember when we did polar, and even in cylindrical, we always had to throw an r in there. Well, anytime you convert to spherical, you're going to have to throw a rho squared sine phi. Always remember to put that in when you go to spherical. In the next section, 12.8, I'll actually talk about where that comes from. All right, so I think it's time for us to do an example. So let's do the triple integral of e to the square root of x squared plus y squared plus z squared with respect to volume, where e is the region in the first octant between the spheres of radius 4 and 9. So what I have here is I'm looking in the first octant. Only in the first octant. I have a sphere of radius 4. So let's say here's 4, here's 4. And we know we have a sphere. So it's going to be, that's the first, just the first octant portion of that sphere. And then we have another sphere, which has a radius of 9. Up here at 9. So it's going to go like this, like that. And it's the region between the two. So this is exactly, well, not exactly, but very close to this picture I showed you a second ago, right? Except in the picture I showed you, the radius that we had was 1 and 2. Here it's 4 and 9. So it's this picture with that scooped out piece. It's the stuff in between. So we should be able to define that region pretty easily in spherical coordinates. So in spherical, we're going to have that phi is between 0 and pi over 2. That theta is between 0 and pi over 2 also. And this time rho is stuck between 4 and 9. And now what we do is we try and set up this triple integral with spherical. So I look at this triple integral over E, and now I know it's going to be triple integral. I know I'm going to have these restrictions. I'll worry about the order in a second. E to the square root of x squared plus y squared plus z squared. Well, remember earlier when I had this note up here that there was a nice equation right here. Rho squared is x squared plus y squared plus z squared. So if I take the square root on both sides, right? This inside piece right here is x squared plus y squared plus, x squared plus y squared plus z squared. That is rho squared. Take the square root, you just get rho. So when I convert that to spherical, that's just going to be e to the rho. And then because I'm switching to spherical, I have to put in that special thing, which is rho squared sine phi. And then my order of integration doesn't matter because these are all constants. So I'll go d rho, d phi, d theta. And then my limits of integration here, 0 to pi over 2. It's my restriction on theta. Phi, 0 to pi over 2 again. And then rho goes from 4 to 9. And that's the integral that I need to do. All right, so if I was going to do this, I'd first integrate with respect to rho. So remember, sine phi is going to be a constant here. I need to integrate e to the rho times rho squared. And to do that, I'm going to use integration by parts. So I think at this point, I'll leave you to this to take it the rest of the way, because we've done triple integrals already. This is really just a matter of converting to spherical, making sure you get all the pieces of the integral set up properly. Yeah, I'll let you have that. All right, let's look at the next example. Oh, well, actually, that's the work for it. Don't worry about that. And then that's the homework assignment. You know what? Since that's all I have to talk about with this, and there's some more videos with examples, let me go ahead and work this one out. I'll go ahead and do that. So I want to do the integral of e to the rho squared d rho. And I know that I have a sine phi here, but I'm going to ignore it because it's a constant. What I would do is I would set up integration by parts. I let u be equal to rho squared. I'll let dv be equal to e to the rho d rho. And then du is 2 rho d rho. And then v would be equal to e to the rho. So by the formula for integration by parts, this will turn into u times v, so rho squared e to the rho, minus the integral of v times du. So notice I have a 2 there. 2 rho e to the rho d rho. And I can pull that 2 out. So I'm done with this for now. Pull the 2 out. Rho squared e to the rho minus 2 integral rho e to the rho d rho. And I have to do integration by parts again. So u is going to be rho. dv is going to be e to the rho d rho. Du is equal to d rho. And v is equal to e to the rho. All right, so now what we do is this piece right here, which is just this right here in brackets, is going to turn into this times this minus integral of this times this. So I'm going to try and write that over here. I have rho squared e to the rho minus 2 times in brackets rho e to the rho minus integral e to the rho d rho. And the antiderivative of e to the rho is itself. So this just becomes rho squared e to the rho minus 2 times rho e to the rho minus e to the rho. And then I can distribute. So going back to this triple integral, here's what I know. This is equal to integral 0 to pi over 2, integral 0 to pi over 2, and then that inside piece, the antiderivative of this, is all of this. I'll distribute the 2 through in a second, but remember I had a sine phi there. So it'll be, I'll just put the sine phi here, sine phi times rho squared, e to the rho, that's this, minus 2 rho e to the rho, and then plus 2 e to the rho. And I'm evaluating that from rho equals 4 to rho equals 9. And then I still have d phi d theta. So I've got to replace all my rows with 9 and then all my rows with 4 and then subtract. So let me try that. This is going to be integral 0 to pi over 2, integral 0 to pi over 2. All right, let's plug in 9 for rho. I'm going to have sine phi times All right, 9 squared is 81 e to the row, but row's 9, so e to the 9th, minus, let's see, 2 times 9, 18, e to the 9th again, and then plus 2e to the 9th there. That's what I get when I plug in 9. Then minus, again, sine phi, and then plug in 4. So 4 squared, 16, e to the 4th, minus 4 here, we get 8, e to the 4th, and then plus 2e to the 4th. All right, d phi d theta. All right, this should simplify a little bit. Integral 0 to pi over 2, integral 0 to pi over 2. All right, sine phi. And then, let's see, 81 of these. 81 plus 2 of them is 83. So 18. 83 minus 18, right? 83 minus 18 is going to give you 65. So we get 65 e to the 9th. I'm going to write it this way. 65 e to the 9th sine phi minus over here, you get 16 of these minus 8. That's 8 of them plus 2 is 10 of them. So 10 e to the 4th. 10 e to the 4th sine phi, like that. And then d phi d theta. All right, that looks okay. Now we integrate with respect to phi. Excuse me real quick. Okay, so we're going to integrate now with respect to phi. Notice also that 65 e to the 9th minus 10 e to the 4th, these are both constants. So what I could do is this. I could just factor out a sine phi like that, right? I'll move it over a little bit. Factor out that sine phi. That'll be a little bit nicer to integrate. Just be one integral to worry about, one antiderivative. So like that. And now antiderivative of sine of phi is going to be negative cosine phi. So integral 0 to pi over 2 times negative cosine, well, yeah, cosine. It's going to go a little faster, but I'll just do this. This is all a constant, so it just came along for the ride. I'm evaluating this from phi equals 0 to phi equals pi over 2. Then d theta. So let's talk about what cosine, let's plug in pi over 2. Cosine of pi over 2, right? Cosine of pi over 2 is 0, right? So that just zeroes out, the whole thing zeroes out. And then we plug in 0. So I'm getting 0 when I plug in pi over 2 minus, now let's plug in 0. Cosine of 0 is 1, but then it's negative, so it'll be negative 65 e to the 9th minus 10 e to the 4th. And then I'm going to integrate that with respect to theta. So all that happens here is that this minus and minus become a plus. The 0 doesn't matter, so it's really just this. And you're integrating it, that's a constant, right? So you're integrating constant with respect to theta. We should just get that number, 65 e to the 9th minus 10 e to the 4th theta, that's the antiderivative of that, from theta equals 0 to pi over 2. And of course, when we plug in 0, we don't get anything, but when I plug in pi over 2, it's all of this times pi over 2. So the answer should be 65 e to the 9th minus 10 e to the 4th, all of that times pi over 2. And that should be it. Now I'm going to double check that because I think I did do that with the computer. Yeah, they went in and simplified it a little bit, but this is the answer right here. So if I take this and distribute it to each one of these, I'll get 65 e to the 9th pi over 2 minus when I distribute here, the 10 and the 2 reduce out, you get 5 e to the 4th times pi. So that answer matches this one, so we feel good about it. That's basically it. Now, for your homework, again, look at those problems that I had assigned there, and you'll get some practice. The difficulty, I think, most of the time is just first getting the correct region, all right? So you'll see in the homework how that works out. And that's it. That's all the notes I'm going to give you for spherical coordinates. Okay, we're going to talk about Chapter 12, Section 8, which is change of variables. And there are lecture notes online, but I'm going to try and simplify everything here with a picture. What we're doing is we're taking a double integral over some region R, and this actually extends to triple integrals also, but it's easier to draw a double integral region of integration than it is to draw a triple integral region of integration. So with that in mind, we have a double integral over some region R. Our variables are x and y. And we look at this double integral and we say, okay, maybe this region of integration is very challenging. Maybe we can't represent it easily as in Cartesian or polar. Maybe it's not a type 1 or a type 2. So we're having some trouble with this region. Then what we want to do is change the variables to some new variables and hope that that new region, when we switch over, is easier to integrate. The other reason we might want to change variables is if the function we're trying to integrate is difficult. If this is tough to do, then maybe if we switch it to a new function of changing the x and y to some new variables, maybe that new integration is easier for us to handle. So that's usually the two main motivations for doing a change of variables. So what we have to assume here is that we are going to have some way of determining what we're going to change the variables to. So I know that I can switch my x over to some function of u and v. That way all my x's get replaced with something, right? So my x is going to become some function of u and v, which I will call x of uv. So x becomes some function of u and v, and also the y, everywhere I see a y, I'm going to change that to a function of u and v. Now these functions don't necessarily have to be the same. So what I'll do is I'll just replace x over here with some function of u and v, and y with some function of u and v, and then I should be able to integrate over this new region. But the big thing from the big idea here from change of variables, that when you do this change of variables, we don't just replace dA with dA. We have something else happens here. So the idea is that you take some infinitesimal region in here, right? And we need to know the area of that. So that has some area to it. I'll call it dA because it's infinitesimal. And when we switch it through this transformation, because x and y changed, that little dA also changes. And what it turns into over here is going to be what's called the Jacobian. So this is, I'm just going to put a capital J here to represent the Jacobian. And then we'll have, with respect to the two variables, u, v, or you could, depending on what the region looks like, you could have that those integration variables switch places. But this Jacobian, what it does is it's kind of like the give and the take. You're allowed to switch the variables over to something new, but you may have to multiply these differentials by something to make the scaling of the region over to this, either the shrinking or the contracting or the deforming of that region. To make it work, you've got to have this factor in here of j. So what is j? That's the next natural step, is to ask what is j. So before I can begin that, figuring out what j is, let me just talk a little bit about an example, I guess, to kind of show you from Cal 2 that you were actually doing this before. Okay, so I'm going to show you a simple result. Let's say we were trying to integrate in Cal 2 something like x cosine of x squared dx. So if we were doing something like this, what we would realize is that if we let this be u, this is almost the derivative of it. So we make a substitution. U is x squared. We differentiate. Du is 2x dx. And then we could say half of du is x dx. So we would rewrite the integral. This cosine of x squared would become cosine of u. And then x dx, right here, turns into 1/2 du. So what I want you to notice is that I have changed the variables over, right? I've switched from here a function of x to over here some function of u. So I have made a change of variables, but my dx did not become just du. I had to scale it by 1/2 in order to make this work. So that's what you did in Cal 2, but you didn't really realize at that point that this right here can be generalized more into double integrals, and that we need a way of coming up with this number. Now in Cal 2 it was pretty easy, we could see how to do it here. But here in Cal 3 we need a more general formula for it, and that's what we're going to do here. We're going to establish that formula. But there's one other thing that I need to review with you, and that's this thing called determinants. Now determinants, this is a very general thing. A determinant is a very general thing. It can be used in many, many different applications in many different math courses, engineering courses, physics courses. But the computation for a determinant is pretty universal. So what we do is we start with a matrix, and we're gonna look at two types here. Let's say we have a 2x2 matrix. So we have a matrix. It has 4 numbers in it. Now these don't have to be numbers, they can be a lot of different things, but for us these are either going to be numbers or functions. So we have a 2x2 matrix, and we put these bars on the side to represent the fact that we are going to find the determinant. So when we do the determinant, this is an algebraic computation. We do a times d minus c times b. CB. And that's it. That's the determinant of a 2x2 matrix. Now, if we do a 3x3 matrix, it's a little different. A 3x3 matrix, we'll have to label this. Let's say it's A, B, C, D, E, F, GH, I guess I'll use I, that's fine. How do we find the determinant of a 3 by 3? So what we do is we start by looking at the top left, okay, and we write that down, A, and we multiply A times a determinant. But this determinant is a determinant of a 2 by 2 matrix, and that 2 by 2 matrix is the one created from those 4 numbers. So one way to imagine it is that we start with A, so we cover up this column, we cover up this row, and then we would get EF, HI, that's the determinant we need here. So this is EF, HI. And that is a determinant that we just did a second ago, 2 by 2. So this becomes A, and then we do E times I minus H times F. And that's it. Okay, so that's the first step. The second step is that we're going to do the same thing for B. But what we'll do is instead of putting positive B here, we actually do the opposite. So we're going to go minus B. And then times another determinant. Now this determinant, what we do is we imagine we've covered up B, so we cover up this column, we cover up this row, and we're left with the DF in the GI. I don't know if you can see that. Cover this up, cover that up. We have DF, GI. So I have DF here and GI. Now of course this is negative B, and then D times I minus G times F. All right, and then we continue. We have one more to do. So we take C, right? And what we're doing is we're alternating here. We have positive A, negative B, positive C, so plus C, and then another determinant here. This determinant, we cover up this column, cover up this row, DEGH. DEGH. So we get plus C times now the determinant DH minus GE. And then you could, if you wanted to, you could multiply the A through here, the negative B through here, the C through here, and that would be your determinant. So that's how you do a 3 by 3. So now let's go back. What's most important there is the method, okay? Now also that method extends out to 4 by 4, but I won't get into that. Okay, so what is the capital J, right? That's the question. What is that capital J whenever we are trying to do our change of variables? Well, capital J stands for what's called the Jacobian, sometimes referred to as the Jacobian determinant. And here's how it works. Since we're only going to be working with double and triple integrals, we're going to have one of two scenarios. We're either going to be changing x and y over to u and v, or if it's triple integral, we're going to change x, y, z over to, let's say, u, v, w. All right, so I'm going to look at each of these cases. So let's try the first case. What if we're trying to figure out what the Jacobian is when we are going from x, y over to u, v? So the Jacobian, the notation for it looks like this. That's the notation for the Jacobian, and here's what it is. It's the determinant, okay? And it's going to be, since we're two variables to two variables, this is going to be a 2 by 2 matrix. It is the partial of x with respect to u, partial of y with respect to u. Oh, sorry, oops, messed that up. Partial of x with respect to v, then partial y with respect to x, partial y with respect to v. So one way you could look at it is if you have two variables, x and y. So you're going to do partials of x across the top, the second row partials of y, and then you have u and v, so this one is with respect to u, then that one's with respect to v. This one with respect to u, and then this one with respect to v. All right, so now, what is that determinant? Well, that determinant is this times this, so partial x with respect to u times partial y with respect to v minus this times this. I'm going to change the order. Partial x with respect to v times partial y with respect to u. So that is the Jacobian of the transformation that takes xy over to uv. Now remember, when you do that change of variables, your x will be some function of uv, and your y will be some function of uv. That's what gives you the switch, the change. And that's what we're doing. These equations that we have here, that's what these partials are. So the partial of x with respect to u will be the partial of this equation with respect to u. Then the partial of x with respect to v is this equation derivative with respect to v, and so on and so forth. So that's your Jacobian for a two-variable change, all right? Now, if you want to do the Jacobian for a three-variable change, then what we're going to have is this. So imagine we're taking x, y, z, and we're switching it over to u, v, w. So x is some function of u, v, w. Y is going to be some function, sorry, I wrote this wrong. X is equal to some function of u, v, w. Y is equal to some function of u, v, and w. And z is also some function of u, v, w. All right, so the Jacobian will be partial, we're switching x, y, z over partial u, v, w. So that's just, again, that's just notation. And this, by definition, is going to be, okay, so my first variable is x. So I'm going to have partial x, partial x, partial x, but then I'm going to go with respect to the three variables, u, v, w. Then I have another row, this time partials with respect to y, or partial of y with respect to the three variables, u, v, w. And then lastly, partial of z with respect to the three variables. So u, v, w, the determinant of that. So what you could do now, I'm just going to set up the first part of this. It would be starting with this, partial x with respect to u times the determinant of this thing, right? Well, you know what? I'll go shorter. So that times this, so partial y with respect to v times partial z with respect to w, so that's this times this, and then minus partial of y with respect to w times that partial z with respect to v. And then I continue. I'm not going to do it all, but the next one would be minus, and then this partial x with respect to v, and then I would have another determinant. So I'd have a total of three of those. And that would be how you change over with three variables. All right, so let me try and generalize this. Okay, suppose you have a function of x and y, okay? And you're trying to do a double integral of this over the region R with respect to area. And you're going to make a change of variables. Your x is going to become x of u, v, and your y is going to become some function of u and v also, then this will be equal to the double integral over s. Now, s is the new region, right, that I showed you earlier, of f with the x replaced with the function, the y replaced with its function of u and v. But then this next part is going to be the absolute value of the Jacobian, all right? And then du, dv, or possibly dv, du, depending on, again, what this new region looks like, what that new region S looks like. So remember this right here, the Jacobian is the partial x, y, partial uv. We showed that earlier. That's notation for the Jacobian. But then we want to take the absolute value of it. So remember, that's a determinant, right? But then whatever your answer is, you want to take the absolute value. So this is the formula whenever you have a switch from two variables to two new variables. Now, if we change this and we make this triple integral with respect to volume, then my x is going to become a function of uv and w. My y is going to be uv and w. And now I have my z is also a function of uv and w. And now this becomes this. I need a w in here. I need a w in here. So my x gets switched over to the new function of three variables. My y gets switched over to the function of the three new variables. My z gets switched over to the function of three new variables. And then I have my absolute value of my Jacobian. And then this will either be like du, dv, dw, or maybe it's du, dw, dv, or maybe it's dv, du, dw, and there's a few more combinations. But the important thing is that this right here is that Jacobian determinant, whatever that is, that's a determinant, and then the absolute value of that. Okay, so what I'm going to do now is I'm going to do a few examples. And the first example I'm going to do is the double integral over the region D of 4x plus 8y dA, where D is this parallelogram. It has the point, let's see, -1, 3. That's the point -1, 3. It has the point 1, -3. It has the point 3, -1. And 1, 5. So it's the parallelogram formed by those 4 points. So let me see, I believe this is going to go down like this. It's going to go down like this, across like that. Okay, there's my parallelogram, that's my D. And we want to do this double integral, but here's the change of variables, okay? We're going to make x be equal to 1/4 u plus v. We're going to make y be equal to 1/4 and then v minus 3u. Now I want to be very clear about something. This transformation, okay, this change of variables is being given to us, all right? This is given. In general, nobody's ever going to give you that change of variables. So a question we'll answer later is, what if you're not given that? How are you going to come up with the change of variables that's going to work? I also want you to notice that x here is a function of u and v, and y here is a function of u and v also. So this is my x is now some function of u and v, and this is now my y here is some function of u and v. All right. Going back over here, we want to know, where does this region go? What does it turn into over here in this new transformation into the UV plane? So what I could do is I could pick a point and I could say, where does that point go? That would take forever though, because I have an infinite number of points. So instead what I'm going to do is I'm going to look at these line segments, okay, for my parallelogram. I'm going to see where they go under the transformation. So my first line segment that I'm going to work with is this one right here. So what I'm going to do is I'm going to try and find the equation of that line segment. So notice that this is a line, right? And so I can find the equation of a line various ways. Notice that my slope, I come down 1, 2, 3, and over 1. So I have a slope. I can say that that line has the equation y equals negative 3x. I know that so far. And it appears to have a y-intercept of 0. So I can say plus 0. That is this green line. Now, if you have 2 points on a line, you can always find the equation doing a more rigorous computation. But just visually, I can tell that's what the equation is. I know that that's what the y-intercept is, so I feel good about that. So my question is, where does that line go under those transformations? So I'm going to come over here and I'm going to take this equation, y equals negative 3x. And I'm going to replace y with this, and I'm going to replace x with this. So let's see what happens. This left side becomes 1/4 v minus 3u. And that equals negative 3 times x, but x is 1/4 times u plus v. And I noticed that because this is multiplication, I have a 1/4 here and a 1/4 here. I'm just going to multiply both sides by 4. That'll give me v minus 3u equals, it'll kill off this 1/4, so I'll still have the negative 3 out here. And then I'm going to distribute it through here. So I'm going to distribute that negative 3 through. So negative 3u minus 3v. Okay, well, what is that? Notice that I have negative 3u and negative 3u, that if I add 3u on both sides, they cancel. So I'm left with v equals negative 3v. And if I add 3v to both sides, I'll get 4v equals 0. And divide by 4, I get v is 0. So what this tells me is that this line segment here under the transformation given is going to turn out to be v equals 0. Well, v equals 0 is like the equation of a line. V is my kind of like the y-axis was over there. So v being 0 corresponds to this line over here, which is like the u-axis. Okay. That's the first transformation. Now let me go over here and try and find where, let's see where this one goes. Okay, so for that one, I think I'm going to spend a little more time coming up with the equation of that. And that's just because I want you to make sure you know how to do the computation. So if we're given 2 points, right, we can find the slope of the line using y2 minus y1 over x2 minus x1. I'm going to say this is x2, y2, this is x1, y1. So if I do negative 1 minus 5 over, 3 minus 1, I get negative 6 over 2, which is negative 3. So the slope of that line segment is negative 3. And then I use this formula, y minus y1 equals m times x minus x1. This was what was called the point slope form of a line. I know m. I know x1 and y1, so this is going to become y minus y1 is minus 5 equals m, which is negative 3, and then x minus x1 is 1. So this is y minus 5 equals negative 3x plus 3, distributing through. And then you get y equals negative 3x plus 8. Now I could have determined that myself. I could have said, okay, well this has the same slope as this one. And then I could have tried to find the y-intercept up here, which would have been 8. But that's how you do it systematically. All right, so this has the equation y equals negative 3x plus 8. And now what I'll do is the same exact thing I did just a second ago. I'm going to rewrite that equation of that line segment. Y equals negative 3x plus 8. And I'm going to replace y with 1/4 v minus 3u. I'm going to replace the other side, negative 3x is 1/4 u plus v, and then plus 8. Okay, so I will multiply everything again by 4, so that'll kill off this one and this one, but this will also be hit by 4. So I'm going to get v minus 3u equals, this is gone, distribute, negative 3u minus 3v, but this time I have plus 4 times 8, which is 32. Notice again that the 3u's cancel, the negative 3u's will go away. Let's move this 3v over, so you get 4v equals 32, and then v must be 8. So now I come back over here and I say, all right, where is v equals 8? So let's say that that's 8 units right there. V equals 8 is another horizontal line. So I've taken these lines that have some slope to them, right? And under this transformation, I've flattened them out. And that's creating what looks like is going to be a rectangle. All right, now I need to find 2 more line segments, the equations of 2 more line segments. Let's do, I'm running out of colors here. I'll do this one in green. Let's do this one right here. Okay, so the slope on this one, I went, let's see, to get to this point, I have to go up 1, 2, and over 1, 2. So that has a slope of 1, y equals 1x. And then where's the y-intercept? Well, if I go up 1 over 1, up 1 over 1, if the slope is 1, then to get to the y-intercept, I go back 1, down 1, which would put me right here. It's 1, 2, 3, 4. So negative 4 is the equation of this little line segment. And then I'll come over here and do the same thing. So y equals x minus 4, and y is 1/4 v minus 3u equals x, which is 1/4 u plus v, then minus 4. Multiply everything by 4. V minus 3u equals u plus v. And I multiplied that by 4, minus 16. And this time, notice that if I subtract v on both sides, it goes away. And then I'll move this u over. I get negative 4u equals negative 16. So u must be 4. So u is 4. How are we doing on time there? Yeah, we're okay. U is 4. So this time over here, u is 4. I'll use blue. U is 4 is about right here. And it's a vertical line. U is 4. And one more line segment to go, and I'll have the new region. So this one right here, the slope of that is also going to be 1. And the y-intercept, I kind of drew it wrong. It hits right through there. So it's up 1 over 1. That should be at 4. So plus 4 here. So when we come over here, the only difference is that this is going to become plus 4, plus 4, plus 16, plus 16. Divide through by negative 4, you get negative 4. So instead of u is positive 4, I get u is negative 4. So check out that region over there. I've taken, this wasn't real complicated, but if we were to try and integrate over this region, we'd have to break it up into, like, you know, type 1 and then do several different integrals or different regions, that is a really nice region to integrate. So what I've done at this point is I know my new double integral, my restrictions on u between -4 and +4, my restrictions on v are between two constants also, 0 and 8. So this is going to be a really nice integral as far as the limits of integration. But I need to now go and transfer this double integral into the new double integral. And when I do that, all my x's have to be replaced with the function, all my y's have to be replaced with the function for y, and I need the Jacobian in there. So let me go after the Jacobian right now. Okay. So remember, what I'm doing is I'm taking this, turning it into a new double integral over some region. I'm going to call that S, and I'm going to have my original function in here 4 with x plugged in, which is 1/4 u plus v, and then plus 8 times y, which is 1/4 v minus 3u, and then whatever all that is, times the absolute value of the Jacobian, which is this, and then d, in this case it won't matter, du dv or dv du won't matter because those are both variables are stuck between constants, so order of integration doesn't matter. So I'm just going to go try and get this now. So what is my Jacobian? Well, Jacobian, partial xy, partial uv is equal to the determinant of partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v, which we said just a second ago was this times this minus this times this. So partial x with respect to u times partial y with respect to v minus partial x with respect to v times partial y with respect to u. All right, so I need to take some partial derivatives now. What is the partial of x with respect to u? So here's my, I'll leave that there. Here's my x. Let me just distribute that 1/4 through. 1/4 u plus 1/4 v. Y is equal to 1/4 v minus 3/4 u. All right, so what is the partial of x with respect to u? So this is a constant. Derivative of this with respect to u is 1/4. Partial of y with respect to v is partial of this with respect to v, which again is 1/4. Minus the partial of x with respect to v, which is, let's see, 1/4. And then times the partial of y with respect to u, which is here, derivative of that is -3/4. All right, let's clean this up. 1/4 and 1/4 is 1/16. Minus over here, -3/16. Which the minus minus becomes plus, so you have 4/16, which is 1/4. So this becomes, I think I'm ready to write this out. This double integral becomes double integral. I'll put the limits of integration on in a second. I already switched my x's and y's over, so let's kill that off. That's just u plus v. And then multiply that through to here, that's a 2. Then pass that through, you get 2v minus 6u plus 2v minus 6u. And then I need the absolute value of the Jacobian. And this is the Jacobian 1/4. And then your du dv or dv du doesn't matter. I'll do du dv. The restrictions on u were between -4 and 4, and the restrictions on v were from 0 to 8. So my Jacobian on this one, the Jacobian determinant, the magnitude of it, the absolute value of it, is just 1/4. That turned out to be a constant. It's not always going to be a constant. So I could pull that 1/4 out, which I'll do. 1/4 integral 0 to 8, integral -4 to 4. Let's see, u's I have -5u, v's I have 3v. I'm going with respect to u, then v. So let's take the antiderivative of the inside with respect to u. So you're going to get -5/2 u squared, and then the antiderivative of this with respect to u is plus 3vu. Evaluating from u equals -4 to u equals +4. Then I'll integrate with respect to v. All right, so if we plug in If we plug in 4 for u, we get 16 here. Divided by 2 is 8. 8 times -5, you get -40. If I plug in 4 here, I get 12v plus 12v. Then minus, now plug in -4. If I plug in -4 here, that's squared, I still get 16, then half of that is 8, and then so I still get -40 there. And then here, -4, I get -12v. And then dv. And I believe this -40 cancels out with that negative is positive, so that -40 is going to be gone. This is going to become plus 12v. I already had a 12v, so I should be looking at this. 1/4 integral 0 to 8 of 24v dv. Go ahead and pull the 24 out. Just make that a 6 out here. Why not, right? The antiderivative of v is going to be 1/2 v squared, but then times 6. So 3v squared, evaluated from v equals 0 to 8. And 8 goes in there, 64. 64 times 3, 180, 192. And then 0 goes in here, you get 0. So 192 is the value of that double integral. That's a lot of work, okay? I understand that. I agree that that's a lot of work. This is more just to show you how it works rather than trying to convince you that this was the more efficient way for this problem, all right? Maybe this problem, we should have just left it in Cartesian. Maybe it would have worked a little better, or a little faster maybe, all right? But again, it's just the method that I'm looking at here. Okay. Okay, so I'm going to do another one here. Let's do the double integral over d of e to the x plus y over x minus y with respect to area, where d is this trapezoid given to you with these points as vertices. 1, 0, 2, 0, 0, -2, and 0, -1. So your region looks like this. That's D. Okay, so what we're trying to do is do this double integral. In this problem, no transformation is given. So let's see why we wouldn't want to do this double integral. Let's say we were able to write this as a type 1 or a type 2 or some combination of those. Integrating this with respect to y or with respect to x would be very challenging. So it doesn't look like I want to do that. So I need to come up with a transformation. Well, it's difficult in this sense to figure out what you need that to be. Like you need to write x as a function of of u and v, and y as a function of u and v. But if I just kind of make a wild kind of educated guess here, what if I let u be x plus y and v be x minus y? If I do this, then this integral becomes e to the u over v, right? It would become e to the u over v. And if I have to integrate that with respect to u, that would be relatively easy to do. And with respect to v, it might be a little harder, but I know I can do that with respect to u. I could not do that when both variables appeared in the top and bottom. So that might be a good first shot at this. But remember, I need to write x as a function of u and v, and I need to write y as a function of u and v. Right now, I've written u as a function of x and y, and v as a function of x and y. So let me switch these over to look like this first. So what I'm going to do, I can take u equals x plus y. I can take this equation right here and solve it for x. So this is x is equal to v plus y, right? So if I rewrite this, this is u is equal to v plus y, right? That's what I get there. So u is equal to v plus 2y. But, well, yeah, I guess I could do it that way. You know, I still need y. Well, if I solve this for y, I have y as a function of u and v. There we go. That's what I can do. So u minus v, if I subtract, I get 2y. And then multiplying both sides by 1/2, I get y is equal to 1/2 u minus v. So notice y is now a function of u and v. Then I'm going to figure out what x is. So let's go up here to this equation we had for x. X is v plus y, but y we just said was that 1/2 u minus v. Let's distribute the 1/2 through 1/2 u minus 1/2 v. So x is equal to v, and then, oh, sorry, take a v and subtract a 1/2 v, I get another 1/2 v. 1/2 v plus 1/2 u. So x is equal to 1/2 u plus v. So there we go. We've got our two x and y equations, both in terms of u and v. So this was kind of my guess as to what I was going to replace these with, and then I was able to convert those into what I needed. So x is equal to 1/2 u plus v, and y is equal to 1/2 u minus v. All right. Now I'm ready to try and transform that region. So I want that to be transformed into some region over here, uv. And when I look at this, I've got to figure out what these equations are. So that little line segment right there, that's the equation x equals 0. And notice that my y values are between -1 and -2. So if I come over here and I write down x is 0, that gives me that 1/2 u plus v equals 0. That's this first equation. And then that means u plus v equals 0 if I multiply both sides by 2. So u must equal -v. Or you could say v must equal -u. I think I'll use this one instead. That looks a lot like y equals -x. So that's just a line with the slope -1. But it goes like this. This is v equals -u. Then I'm going to take this one because it's easy. Remember, this was x, this was y. This is y is 0. So if I write down y is 0, we use this equation, which changes that to a minus, changes that to a minus, changes that to a plus and a plus. So you get basically v is u. which would look like this. The diagonal, v is u. And now let's look at this one right here. So the slope of that line, you go up 2 over 2, so it's y equals x. And then the y-intercept here is negative 2, so x minus 2. So I'm going to write this down. Y equals x minus 2. So y is 1/2 u minus v equals x, which is 1/2 u plus v minus 2. Multiply everything by 2. And then notice the u's cancel. I'll move my v's to one side. Negative 2v equals negative 4. So v equals 2. So v equals 2 over here. Like this. And then I'll do the same thing for this line segment here. That again has a slope of 1, has a y-intercept of negative 1 though. So if I come over here and change this, the only thing that changes is this is a minus 1. This is a minus 1, and when I multiply both sides by 2, I get 2 here, which gives me negative 2 there, and then minus 2 there, and then here it'll be 1. So v is 1 is my other line segment here. And it's the region bounded by all 4, so it should be this region right there. And that may not look like a better region, okay, but I think our integration is going to be easier. So would you look at this as a type 1 or a type 2 region back from the integrals when we first started doing double integrals? Well, type 2, right? Because I draw an arrowed segment there, turn my head. This one is always, as I move this up and down, this function always stays on this side of the arrow. This one's always on the bottom side. And my v values are between 1 and 2. So I know v goes between 1 and 2, and my u's are between 2 functions of v. This one right here is u is v. So the one on the right is u is v. And this one right here is v is negative u. If you solve that for u, it's u is negative v. So this is negative v. So it's stuck between those two. All right. What else do we need? I have my limits of integration. I have how that's going to switch over. Now I need the Jacobian. So let's get the Jacobian. Jacobian is going to be this, which equals partial x with respect to u, partial y with respect to v, minus partial x with respect to v, is partial y with respect to u, without going through all that work again. Partial of x with respect to u is going to be 1/2. Partial y with respect to v is negative 1/2. Minus partial x with respect to v is 1/2. Partial y with respect to u is 1/2. So you get negative 1/4 minus 1/4, which is negative 1/2. So I'm ready now to rewrite the double integral. This double integral I'm going to go du dv, because v has limits 1 and 2. U has limits negative v and v. And then I'm integrating e to the u over v. And then I need the absolute value of my Jacobian. Negative 1/2. Absolute value. That's positive 1/2, and that can come out. So 1/2 integral 1 to 2 integral, well, yeah, integral negative v to v. E to the, I'm going to write that as 1 over v times u, and then du dv. And the reason I'm doing that is because I'm about to integrate that with respect to u. And when I do that, I'm going to treat v like a constant. So 1 over v will be a constant. So this is 1/2 integral 1 to 2. Antiderivative of e to the 1 over v u is going to be v e to the 1 over v u. So just think about it. What's the derivative of this with respect to u? That's a constant. Ignore it. Derivative of that is itself times the derivative of what's up here with respect to u is 1 over v. So 1 over v pops out, hits that v, goes away, and that would leave you with this. So that's the antiderivative. Evaluating from u equals negative v to u equals v. And then I'll integrate with respect to v. So this is equal to 1/2 integral 1 to 2 of, let's see, plug in v for u, and you get 1 over v times v, that's 1. So you get v times e to the 1, so v e to the 1, that's fine. Minus, and then now plug in negative v, you get v e to the negative 1 and dv. All right, next step. Just remember e to the 1 and e to the negative 1 are constants. So I'm going to go ahead and take an antiderivative now. Antiderivative of this with respect to v is 1/2 v times e to the 1. Antiderivative of this with respect to z is minus 1/2 v. I forgot to put v squared, sorry. V squared e to the negative 1. And I'm evaluating this from v equals 1 to 2. So let's let v be 2. 2 squared is 4. Half of 4 is 2. So I get 1/2 2 e to the 1. Now when I plug in 2 here, I get the same thing. Minus 2e to the negative 1. Okay, that's what I get when I plug in 2. Minus 1/2, let's plug in 1. So you get 1/2 e to the 1 minus 1/2 e to the negative 1. Now let's distribute this through. This 1/2, you get e to the 1 minus e to the negative 1. Let's distribute this through 1/4, but then you're subtracting, so minus 1/4 e to the 1, and then this is going to be minus 1/4, but then plus, so plus 1/4 e to the negative 1. And you can combine these two together and these two together. So you get e to the 1 plus, or yeah, e to the 1 minus 1/4 e to the 1 is 3/4 e to the 1. I'm just going to write as e. And then negative e to the negative 1 plus 1/4 e to the negative 1 is minus 3/4 e to the negative 1. This is the same as 3/4 e minus 1 over e. All right, that's it for that. So I do a couple of these on homework, but now I'm going to take a little bit more time. I want to show you where, if you recall, whenever we were doing conversions from Cartesian to polar coordinates, right? If we had a double integral over some region R of f of x, y, dA, and we wanted to go to polar, we would go double integral over some region, I'll call it S, f, and what we did is we replaced x with r cosine theta and y with r sine theta. And then we said we always had to put this r in there. And then it was either like dr d theta, or it might be d theta dr. But we said, you know, this r had to be there, and tried to explain a little bit where it came from. But what I want you to see now is that this is actually the Jacobian, okay? It's the magnitude of the Jacobian. And so what I'll do is I'm just going to convince you of where that r came from. What were our transformations? X was equal to r cosine theta, y was equal to r sine theta. Now I could have written x is equal to like u cosine v, y is equal to u sine v. So I could have used u and v, but we used r and theta because geometrically the r and the theta made sense. So I'm going to stick with r and theta. So the Jacobian is going to take xy over to r theta. And so that will be this determinant, partial of x with respect to r, partial x with respect to theta, partial y with respect to r, partial y with respect to theta. And then by definition, this is partial x with respect to r times this, partial y with respect to theta minus this and this, partial x with respect to theta, partial y with respect to r, which is, well, what is the partial of x with respect to r? So what's the derivative of this if we treat r like the variable and theta like a constant? It's just going to be cosine theta times partial of y with respect to theta. So this time r is a constant, theta is a variable, derivative of sine theta is cosine theta, but I have an r in front of it, so r cosine theta. I'm running out of room. Let me do that over here. So where are we? We're at cosine theta times r cosine theta. Then we say minus, what's the partial of x with respect to theta? So what's the derivative of this with respect to theta? Well, the r comes along for the ride. Derivative of cosine is negative sine. So I get negative r sine theta. And then the partial of y with respect to r. So I'm treating now theta like a constant. There's my variable. Derivative of that is just going to be sine theta. And when I clean that up, I get r cosine squared theta plus, because I have two negatives, r sine squared theta. And if I take out an r, factor out an r, I get cosine squared theta plus sine squared theta, which is 1, and so r times 1 is r. So your Jacobian, you take the absolute value of that, you just get r. So, well, absolute value of r is just r because r was the radius, and the radius we're going to assume is positive. So that's where the r comes from in polar conversion, which is pretty cool. Now, last section, and this is probably the hardest thing to show you, it's going to take a while, but in the last section, we did spherical. And remember when we did spherical, we always had to throw something into that triple integral. Remember, it was rho squared sine phi. That was that thing we had to throw into the triple integral anytime that we went from Cartesian to spherical. So I'd like to show you where that one comes from. So what you have to do is first remember what was the conversion that we used in spherical. Write them down, make sure I got them right here. Our conversions for spherical are x equals rho cosine theta sine phi. Y is rho sine theta sine phi. And z is rho cosine phi. Those were our conversions. So in order to I'm trying to prove to you that this was the Jacobian. The Jacobian, if we're going from x, y, z over to what? Rho theta phi will be equal to the determinant of partial x with respect to rho, partial x with respect to theta, partial x with respect to phi. Then partial y with respect to rho, partial y with respect to theta, partial y with respect to phi. Partial z with respect to rho, partial z with respect to theta, partial z with respect to phi. I need the determinant of that. Nasty. This will be equal to, okay, see if you can follow me on this. I'm going to write it down here low. Partial x with respect to rho which is this one, times the determinant of this. So the determinant of that is partial y with respect to theta partial z with respect to phi minus partial z with respect to theta partial y with respect to phi minus, because remember that's what you do, you switch. Now I'm doing this one, so partial x with respect to theta times the determinant. I cover up this column. I'm doing determinant of these two and these two, so that and that. So partial y with respect to rho, partial z with respect to phi, minus partial z with respect to rho times partial y with respect to phi. Okay, plus this one right here, partial x with respect to phi times the determinant of this little 2 by 2. So partial y with respect to rho, partial z with respect to theta minus partial z with respect to rho, partial y with respect to theta. Okay, if I could just compute that, I'll have the Jacobian. So that's going to be a mess. Now I'm going to need some things here in order to do this. I'm going to need the partial of this with respect to rho, partial of this with respect to theta, partial of this with respect to phi. So let me get all of those and just put them next to it. The partial of x with respect to rho equals, so this is our variable, everything else is a constant, cosine theta sine phi. Okay, what is the partial of x with respect to theta? Well, this time treat rho and sine phi like constants, so derivative of cosine theta is negative sine theta. So I'm going to get negative rho sine theta sine phi. Okay, then I need the partial of x with respect to phi. So I'm just taking derivative of sine phi, which is cosine phi, and that's a constant. So rho cosine theta cosine phi. I also need all the partials for y. So the partial of y with respect to rho is sine theta sine phi. Partial of y with respect to theta, I just take derivative of sine theta as cosine theta, so rho cosine theta sine phi. Partial of y with respect to phi is rho sine theta cosine phi. So that was the derivative of sine phi is cosine phi. And I need all the partials with respect to, or of z. So the partial of z with respect to rho equals cosine phi. The partial of z with respect to theta is 0 because there is no theta here. And then the partial of z with respect to phi is negative rho sine phi. Okay, remember our goal here is for me to show you that the absolute value of the Jacobian is going to turn out to be that. All right, what a disaster. All right, let's see if I can get this. Which of these are 0? Partial z with respect to theta. Here's partial z with respect to theta, right? So this is all 0. This whole thing gets zeroed out. So when you do this first distribution here, it's going to zero out. Then over there, it's not. So what I'm going to do is I'm just going to tweak this formula a little bit. I'm just going to go this. It's going to be this times this, right? That might make it a little bit easier. That's the only place that partial z with respect to theta appears. All right. Partial of x with respect to rho. This right here. Cosine theta sine phi times, let me try and do this distributing all at one time. This times this. Partial y with respect to theta is right here. So times rho cosine theta sine phi. But then this was also multiplied partial z with respect to phi, which is times negative rho sine phi. Just remember, this is all multiplied together. So it's that times that times that. Okay, that's just this distributed through. Now this to here is going to be minus. You're going to have this again, so cosine theta sine phi. But this time times negative, or wait, I already did minus, hold on a second. Yeah, I already did the negative, so it's that times this and this. Cosine z with respect, cosine z with respect to theta. We had it twice. Oh, that's 0. Bam, that's awesome. Okay, I didn't recognize that before. That's gone also. So I don't have this second multiplication, so I don't have that piece. Good. All right, let's do this one now. Here to here. So we do get minus. Partial of x with respect to theta is this. Negative rho sine theta sine phi. But then you're also multiplying that times partial y with respect to rho, which is sine theta sine phi. But then you're also multiplying times this partial z with respect to phi, negative rho sine phi. Okay, so I've taken care of this. Now I've got to go this to this. Negative negative is plus. Partial x with respect to theta, negative rho sine theta sine phi, running out of room. And then partial z with respect to rho, cosine phi. And then partial y with respect to phi is rho sine theta cosine phi. And I still have to do this one over here, but I'm out of room. So I'm gonna squeeze it in here. It's gonna be this times this. So it'll be negative partial x with respect to phi. Here, rho cosine theta cosine phi times partial z with respect to rho cosine phi. And then partial y with respect to theta, which is rho cosine theta sine phi. All right, that is it. Now let me clean this ugly thing up. Okay, let's look at the rows here. We have rho here, negative rho here. That's negative rho squared. Okay, cosine theta, so I have cosine squared theta. I don't have any sine thetas, but I have sine phi, sine phi, sine phi, so sine cubed phi. You know, I think I'm going to write this above. Easier for me to write. So I have negative rho squared cosine squared theta sine cubed phi. Okay, that's what I get when I put all this together. So I'm done with that. Okay, over here, let's see, negative negative is plus, but then negative again, so I have negative. I have rho and rho again, so that's rho squared. Okay, I have sine theta, so sine squared theta. I have sine phi, sine phi, sine phi, so sine cubed phi again. And that takes care of this. Okay, let's do this one right here. I've got negative rho and rho, so negative rho squared again. I've got sine theta, so sine squared theta. I have sine phi, cosine phi, cosine phi. So sine phi cosine squared phi. And then the last one, negative rho and rho, negative rho squared cosine theta, which is cosine squared theta. I have cosine phi, sine phi. So that's sine phi cosine squared phi. That takes care of the last ones. So I should have 4 pieces up there, which I do. And now I've got some really cool things happening here. Greatest common factor, just look at these 2 terms right here. Right here. They both have a negative rho squared. They both have a sine cubed phi. So I factor that out of both. And when I do that, I'm left with, if I take negative rho squared and sine cubed phi, I'm left with cosine squared theta. If I do the same thing over here, took out the negative rho squared and sine cubed phi, I get plus sine squared theta. And we all know this is 1. So that's going to be real nice over there. Over here, if I focus my attention on these, they both have a negative rho squared. I can pull that out. They both have a sine phi cosine squared phi. So I'm going to pull out a sine phi cosine squared phi. If I do that, I'm left with a sine squared theta plus a cosine squared theta again, which is a 1. That's beautiful. So I'm left with negative rho squared sine cubed phi minus rho squared sine phi cosine squared phi. And notice that these both have a negative rho squared sine phi as a common factor. I pull that out, I'm left with sine squared phi plus cosine squared phi, which again is 1. So you're left with negative rho squared sine phi. And then this is the Jacobian. Then if we take the absolute value of this, we get rho squared sine phi, which is your conversion factor whenever you're doing spherical coordinates. So I hope that that was kind of cool to see. It's a nice derivation, and it shows how to use that Jacobian determinant on 3 by 3. So switching from 3 variables to 3 new variables. Okay, that's it for this section. Do your homework and you should be good.